Okay, let's dive into this explainer and honestly completely shift how we look at complex, intimidating geometry problems. Because if you've ever looked at a bizarrely shaped object and thought, there is absolutely no mathematical formula for that, well, you're exactly in the right place. Today, we're taking a real masterclass in deconstruction. We're specifically looking at how we calculate the surface areas and volumes of combined solids. Basically, we're going to take things that look totally impossible to measure and break them down into simple, manageable pieces.
Just think about a truck carrying oil down the highway, or maybe picture a standard test tube from a chemistry lab. We interact with shapes exactly like these all the time. They're literally everywhere. But here's the catch, right? They aren't just simple spheres, and they definitely aren't your basic cylinders or cones. They're hybrids. They are combinations of those basic solids we've all tackled in earlier geometry classes. And so this brings us to a massive roadblock. I mean, if you open up any standard math textbook, you'll easily find a formula for the surface area of a cylinder, sure, and a formula for a hemisphere. But if there is no single magical textbook equation for a test tube, how exactly are we supposed to figure out its surface area or its total volume? How do we actually measure a shape that just completely defies a single formula? So here is our agenda for today. 1. Solids in real life. 2. The deconstruction strategy. 3. Calculating total surface area. 4. Figuring out total volume. And finally, 5. Testing your knowledge. All right, moving right along to Section 1, Solids in Real Life, and Section 2, the Deconstruction Strategy. So, treating math like a Lego set is pretty much your ultimate lifeline for this chapter. Because truly, the absolute secret to mastering this is changing how you see the objects around you. The core deconstruction strategy involves 3 super simple steps that will transform an impossible shape into a combination of basic building blocks you already know. Step 1, identify the basic shapes hiding within that complex solid. Step 2, determine the area or capacity of those individual blocks. And step 3, cleverly combine your standard formulas to get the final answer. See, it's all about breaking the complex down into the familiar. This brilliantly illustrates our strategy. Take a look at this seemingly complex top, the classic children's toy. When we just pull it apart in our minds, that toy is really nothing more than a standard cone and a standard hemisphere brought together, right where their flat circular faces touch. By separating them visually like this, we instantly know exactly which formulas we need to pull from our mental toolkit. Now for Section 3, calculating total surface area. Okay, now that we know how to break shapes apart visually, let's look at the absolute biggest trap students fall into in calculating surface area. This is where you really have to pay attention to the physical reality of the object. The crucial point here is that when you join 2 building blocks together, some of their surfaces get hidden. This means, and hear me out on this, you absolutely cannot just calculate the total surface area of block A and the total surface area of block B and just add them together. No way. If you do that, you're counting surface area that literally no longer exists on the outside of the new combined object. Think of surface area like painting. If we wanted to paint that toy we just looked at, the paintbrush would only touch the outside boundary, right? The flat circular bases of the cone and the hemisphere are glued together on the inside. The paint can't reach them. Therefore, the new total surface area of the toy is actually just the curved surface area of the hemisphere plus the curved surface area of the cone. It's really that simple. Let's look at a concrete example from the text. Rashid's playing top. The entire top is 5 centimeters tall with a diameter of 3.5 centimeters. By organizing the given dimensions of our separated building blocks, this whole complex problem just becomes simple arithmetic. The hemisphere has a radius of 1.75 centimeters. Because the total height is 5, we subtract the hemisphere's 1.75 centimeter radius to find the cone's specific height, which leaves us with 3.25 centimeters. From there, we just find the slant height of the cone, which works out to about 3.7 centimeters. Once we have those basic dimensions nailed down, we just plug them right into our curved surface area formulas. Pi times radius times slant height for the cone, plus 2 times pi times radius squared for the hemisphere. By adding just those curved outside parts together, we find Rashid needs to paint approximately 39.6 square centimeters of space. See, deconstruction makes the whole shebang totally manageable. All right, Section 4, figuring out total volume. Now, what's really interesting here is how the rules completely change when we shift from painting the outside of an object to filling the inside. Unlike surface area, which, as we saw, hides connecting faces when objects are glued together, volume is incredibly straightforward. It is purely additive or subtractive. The amount of space inside an object doesn't just disappear because it's touching another object. So if you have two combined solids, you just calculate the total volume capacity of block 1 and add it directly to the total capacity of block 2.
Let's take the real-world scenario of Shanta's industrial shed from the source material. It looks like a massive, complicated building, right? But applying our deconstruction strategy, we can instantly see it's just a rectangular cuboid on the bottom, surmounted by a half-cylinder on the roof. The cuboid base is 7 by 15 by 8 meters, and the half-cylinder on top has a matching diameter of 7 meters and a length of 15 meters. To find the total air capacity of this building, we just calculate both volumes entirely independently.
We find the volume of the cuboid just by multiplying length, breadth, and height. Then we find the volume of a full cylinder and simply divide it by 2. Adding those two distinct whole volumes together gives us a total air capacity of 1,128.75 cubic meters. That's enough space to fill a fairly massive swimming pool. And there are 0 hidden vases to worry about here. Now, obviously, in the real world, if you start packing machinery and workers into that shed, you'd need to subtract their volumes from this total to find the remaining air, hopefully leaving enough room for everyone to breathe. But mathematically, it's all incredibly logical once you break it down.
And finally, Section 5, testing your knowledge. So, we've tackled the tricky rules of the outside and the much more straightforward math of the inside. And let's quickly synthesize everything we've learned. If you take away absolutely anything from this explainer, let it be these 3 golden rules. First, whenever you face a weird shape, always deconstruct it into basic building blocks like cylinders, cones, and hemispheres. Second, when calculating surface area, remember the paint rule. Joining shapes hides the faces where they touch, so rely on your curved surface area formulas. And third, when calculating volume, remember it's all about total capacity. Just find the volume of each separate block and add them all together. Before we wrap up, I want to leave you with a really fun challenge straight from the exercise section. Picture a batch of 45 gulab jamuns. Delicious, right? Now, each one is shaped exactly like a cylinder with 2 hemispherical ends, and they contain sugar syrup up to about 30% of their volume. Using our deconstruction strategy, can you calculate the total volume of just one of those sweets, figure out the volume for all 45, and then find exactly how much syrup is hiding inside them? You have literally all the tools you need now. Break it down, run the formulas, and see if you can solve it. Because ultimately, if you can deconstruct a complex sweet like a gulab jamun, what other complex problems in the world around you are just waiting to be broken down into simpler pieces?